All right. A very good morning to everyone. Let me try this again with the mic on. Very good morning to everyone. And as always, warm welcome to Business Analytics and Data Science. Our third session, I believe. So we already made some good progress. Today, the foundations of predictive analytics are on the agenda. We'll start, as always, with a brief recap of last week to see where foundations of predictive analytics fits in and how it continues what we did last week. So let's quickly revisit where we are and what we did last week. Here we see once more one of my favorite slides, which nicely, I believe, sets the scene for this course. Business analytics in all its flavors. It's always about, remember, the support of decision-making in business organizations, whereby the way decision-making is supported varies across analytics streams or analytics flavors. We elaborated on the descriptive part last week and learned about K-means as a popular way to build clustering models, and we discussed how clustering models that group large and complex data sets try to aggregate the information in such large and complex data sets can help decision-making, can inform decision-making. So basically, when we move on to predictive analytics today, this means we will look at a different paradigm toward decision support. And on that note, this is the second slide I'd like to bring to your attention from last week. It's kind of our map of algorithms or models that are popular in business analytics. By no means a fully comprehensive set of techniques, still a useful, I believe, set of techniques that you want to know about. We have the distinction between predictive approaches and descriptive approaches. So today we look at the left branch here in this picture, and we see that predictive models come mainly in two flavors: regression and classification models. So how these are to be distinguished, that is an important topic for today. And underneath these two types of predictive models, you see a couple of terms. Many you know. Linear regression you certainly all know. I bet many of you also have heard about neural networks or artificial neural networks. In a nutshell, these are the algorithms that we can use, that we find in our software, in our tool set, to build regression or classification models. So we will only look at a few examples of these algorithms today and then further develop our understanding of these techniques in subsequent weeks. And before moving on, I was already informed that there is at least one more question concerning last week. So the question, just for all of us, concerns our example that we introduced last week, the picture about clustering models. We had this two-dimensional attribute space where we had purchase volume or purchase amount. I believe that was the ordinate. Is that right? The purchase amount was on the ordinate, right? So y-axis. Okay, so we had purchase amount by frequency, is that correct? Or number of purchases? Number of purchases, so how many times the customers came in total. I use the hashtag to abbreviate number, so this is number of purchases. And then we had a couple of clusters. One, I believe, was here. Let's use the X for individual data point, and another cluster was located somewhere here. It's maybe a bit extreme. I think my original slide was a bit milder in the value of the attributes, but it was somewhat like that. And then we said, so here is one group of customers that show a certain purchasing pattern, and two more of these. I think one was the orange cluster, and then maybe we also had a green cluster. One was the green cluster, so let's make that the green cluster. And now you said that our labeling of these clusters was somewhat incorrect, the way we interpreted these clusters. Is that what you were saying? It's my problem, people don't listen to me. Basically then in a nutshell, we sort of made the point that anytime this type of result is what we get from cluster analysis, we use a set of observations, put that into our clustering algorithm, and what the algorithm will do for us, it will determine which points, which observations, which customers in my example belong to which clusters. And in order to perform these tasks, we may need to tell our algorithms how many clusters we want, or maybe the algorithm can determine the number of clusters, or at least a sensible number of clusters, which may be a good choice automatically. Hierarchical algorithms like this was the appendix part of the slide book actually, where I put some comments on hierarchical clustering methods like agglomerative clustering methods. They would always provide an indication how many clusters might exist in the data. It's never clear cut, and the non-hierarchical clustering techniques like k-means, which we looked at in a bit more detail, they do not provide an indication how many clusters exist. So for this data situation, if we were using a k-means algorithms, we would need to tell k-means that we seek 3 clusters, and then k-means would probably found exactly these 3 clusters. And that is it. Then the algorithm says done, and now it's our task as analysts to find a crisp definition of these subgroups. What are these customers? What are stereotypes of customers that we could consider to simplify our thinking? Not to think about the entire population of customers, but only to think about the stereotypes and make a decision based on the stereotypes. And possibly there was a minor flaw. I need to look at that. That was the comment with the way I interpreted these clusters, but I think we discussed that last week, what could be a sensible interpretation. For example, here we have the orange cluster that is characterized by a large number of purchases. So the customers come, see our shop often, buy a lot, because they also display a high purchase amount. So there the slide should say something like premium customer, which could be a sensible stereotype, a sensible label to attach to the orange cluster here. Since the customers buy a lot when they buy, and since they buy pretty often relative to other customers, they are certainly good customers, create a lot of value to the company, so we might refer to them as premium customers. As opposed, for example, to the blue cluster, where we have customers that buy a lot when they buy, but don't buy very often. So they buy relatively infrequently compared to other customers. And then the green ones are those that come very often and don't spend a lot. These, I think, we labeled as transactional customers. But this labeling is always a manual step. It's a human element in the clustering process, and because of that, it's subjective to some extent. And I hope that sort of clarifies the point. Let's move on then. My idea would be brief introduction, predictive analytics. What is that about and how does it differ from descriptive analytics? That's the intro part. We look at applications. Thereafter, how can we use predictive models to support decision making, or what are popular use cases in industry? And then the last session, we will revisit, depending how much time is left, decision trees. And you know, when saying revisit, I'm referring to my undergraduate course where I've seen some, maybe several of you. So I believe that for a sizable group of us, this really is a repetition. You have seen decision trees before. For those who see them for the first time, you might feel that I go through them a bit quickly. Still, I believe that the materials that you get is quite informative. And in addition, always remember, we look at these things in more detail in the tutorial as well. You will use R to build your own decision trees, whatever that means. And this will help tremendously with further sharpening your understanding how this exemplary predictive algorithm works. And then, of course, some summary. But let's move on. Introduction. As a matter of fact, that's another slide, the last slide, which was shown last week. The type of data structure we operate in business analytics very often. Very, very simple, just flat table. Rows depicting observations, customers, or whatever it is that we are trying to analyze here. Columns providing the relevant information about the information. Characterizing the customers, as in my example, along certain dimensions, such as demographic information, you see gender here, or transactional information, such as the number of orders, the number of returns that might be an e-commerce setting where people buy online but return some of the items that they purchase because they don't fit, don't function, or they just don't like what they bought before. Days since last order, total purchases, etc. And with this type of data, once we have it, we can immediately use some clustering technique to summarize our data, see how many subgroups of customers exist. And this is what we did last week. Now to move on, we need to augment this table. We need more for predictive analytics. Here I introduce one more column. It's highlighted, it's a special column. I called these purchase. It's a yes-no type of column, and let's imagine that this column depicts for each of the customers whether she has responded by making a purchase to some past marketing action. Maybe we have sent the customer an email saying, look, we are currently have this beautiful pair of jeans, it's on sale, why don't you have a look? And whenever you see a yes in the table, possibly the corresponding customer clicked the link in our email and bought the product. And no could mean either they didn't click the link at all, just ignored the email, or clicked on the link in the email, examined the pair of jeans, but eventually decided against buying. That could be the definition of this purchase. This novel piece of information, as we shall see, makes a fundamental difference. In terms of terminology, again, there are synonyms around. We call that a target variable, or in statistics, that's typically the dependent variable or the response variable, and sometimes it's also called a label. All these terms mean the same thing, synonyms. Again, it creates confusion, but once you got accustomed to these terms, you will be able to immediately just move back and forth and interpret them all as the same thing. The way why I say this is this new column adds a fundamentally different perspective from the perspective we had before. Is if we send these emails out, or more generally, if we plan some marketing action, we typically consider who should receive the action, who is our recipient. For email, email is a delicate example. Sending an email does not cost a lot. So you could say, well, for email marketing, what is the point of targeting email marketing? It does not cost us money, which is it's true. It doesn't really cost a lot of money. However, you could argue that you should target or your email communication, because sending out too many emails that customers perceive as irrelevant will probably dilute your brand, hurt your image, create annoyance on the customer side. So they don't want to receive too many emails which are not relevant. That's a cost that's hard to measure in euros and cents, but it's still a plausible, I believe, argument. And then email is just one channel. Considering a different channel, maybe you don't send customers an email, but you call them, you have a call center agent calling the customer on the phone, trying to market some product, then there is a tangible cost involved. The fixed cost of running the call center and the variable cost of the agent calling the customer that you need to consider. And when you plan these marketing actions, you want to determine who is a good recipient, who is worth the cost, who is worth my investment, worth the time of the call center agent. Trying to allocate marketing budget efficiently dictates that type of targeting. And then, if we were able to anticipate who is likely to buy and who is not likely to buy, if we are able to predict this new column, this light blue column, our target variable, could we predict that? It would be extremely useful to target our marketing actions. We would contact by email, by phone, which channel we like, those customers who are interested and have a high chance of buying, and we would ignore the rest. This will save precious resources, time, money, and at the same time, we avoid contacting customers with information that they don't need, don't see as relevant. And this really is what predictive modeling is about. We have one column, our target, our dependent variable, the value of which we want to know, but can't observe. When we plan a marketing action, when we plan our next call center campaign, we don't know who's going to buy and who's not going to buy. Ideally, we would want to know this, to target our action, but we don't. All we know is what has happened in the past. The other variables. That is what we know. And we can try to use this information, use what we know, what we have observed in the past, to predict what is going to happen, to predict the target variable, to predict what we ultimately want to know, to support decision making. The support here in predictive analytics is a forecast. And targeting, marketing is a popular and intuitive use case to see how this is valuable. I created some slides to really stress that, because I see it as fundamentally important principle of predictive modeling. We have past data, that's a prerequisite, as my example, tabular data, and we have labeled data. This is important. We have labeled data, we have data where the value of the dependent or target variable is known to us because it's past data. If you are into finance, think of stock prediction. It would be lovely to forecast tomorrow's closing price of our favorite stock. Maybe this is Apple, maybe this is Google, maybe this is something else. It would be wonderful if we could forecast tomorrow's closing price. We would get very rich, would not need to spend time sitting in lectures, learning about business analytics. Beautiful, just it's hard. What we know is yesterday's closing price. And we also know the closing price day before yesterday. You can try to use this past information to create a forecast, what's going to happen tomorrow. If you ever make that in stock prediction, I congratulate you. Just know it's hard. I tried, it's hard. And this transition from the past to the present is characteristic. It's instrumental to predictive modeling. The algorithms for predictive learning are called supervised algorithms in machine learning. We can throw them on our label data set, and they produce a prediction model. A vehicle that we can apply. Specifically, our model can be applied to data where we don't know the target, to unlabeled data. Note that in my picture, the light blue column is missing. So the lower table could represent something as the new data, tomorrow's stock price, or new customers that we have not seen before. We don't know their target label. We don't know whether they will buy or whether they won't buy. But we do know, that's the premise, we do know the value of the other characteristics. Then we use our model to process these characteristics, process this known information, and produce a forecast. That's basically the connection. The algorithm is applied to label data. It creates the model. The model is applied to unlabeled data, where we can forecast the value of our target variable. And this is then basically where the story ends of predictive analytics. This is the way we support decision making. In some applications it is useful, then predictive analytics is helpful. And whenever this sort of approach is not useful for decision making, predictive analytics is just not our right approach for decision support, right? A prediction model I wrote is a mapping from known features to an unknown target. Mathematically, you could write that down as a mapping function from the space of the independent variables or the attributes to the space of the target. Well, I opted for the picture, but this mapping, it's the same idea. And often, not always, but often, the point in time where the label data is captured and where the new data is captured come in sequential order. And normally we build our model on past data and apply to novel data, like novel customers. That's a common setting. It's not essential, though, that there is this temporal element of the label data being collected in the past and the data that matters for the application, the data where we apply our model to, that being collected in the present. It's commonly the case, but it's not mandatory. Last bit. Let me amplify that. You also see now the output of our model. The output of our model. Note these ends in the data set on the lower left pane. You have observations n+1, n+2, n+m. Using that to highlight its novel data. And then for each of these observation points, each of these customers or whatever it is, our model produces a forecast of the target. That is the output. So this picture summarizes the whole story of predictive analytics. And then there are multiple algorithms that can be used here. We learn about some of these. And there are some specific processes that we should know about and should follow if we want to use that in industry to make sure that our predictive models really do their job, are good, predict accurately. There are some processes to check that, and these we need to know as well, in addition to the algorithm. But apart from that, this is really the whole story. So this is your map for many weeks to come. And I also tried myself on coming up with a crisp definition
model and algorithm, these terms are often used in a fuzzy way, not clearly delineated. So for my course, the model, the predictive model or prediction model is then, I see it as the result from applying an algorithm to labeled data. That's basically the connection. You see that here. And many examples you know well of such learning algorithms. You don't refer to them maybe, or we're not used to referring to them as a learning algorithms, but you do know them well. Here, for example, we have linear regression. You can consider it a supervised learning algorithm. Clearly was invented long before people started to think and worry about machine learning. But it embodies all the characteristics of a supervised learning algorithm. We have a target. In my example, it's sales. Say we want to predict sales. We have observational data. I use price. The price of a product we can observe. In fact, if we are the supplier, we can control the price. We just set it. And then we can use our model, our mapping from the observed data to the unobserved data of the cells to try and anticipate how much quantity we are going to sell at a given price level. And the reason I picked linear regression is that you also know very well how this model is created. You know, least square, ordinary least squares are something you know by heart, how that works, how we find our regression lines through minimizing the sum of squared residuals, undergrad statistics. At a more abstract level, we can think of this approach as a way to maximize the agreement between our model and the data. By trying to find a good fit of our line to the data. Moving the intercept of the line, changing the slope, if it's really in only 2 dimensions, such that it nicely cuts right through our observed data. This fit maximization, or mathematically speaking, this optimization of some objective function that measures how well our model fits the data is also instrumental to any supervised learning algorithm. We see that in any predictive model. They differ in how they do it. So there are other ways than linear regression, using other techniques to do this optimization, but they all do it. So it's a typical step. And this optimization requires, if you think about it, ordinary least squares requires you to know the value of the dependent variable, of the target variable. Otherwise, you can't calculate squared residuals. That's another way to think or to understand why it is essential to have labeled data to use a predictive learning algorithm. Otherwise, you can't apply these algorithms. You can't carry out this fit maximization. To conclude the introduction, I said there are 2 flavors in predictive modeling, regression and classification. You see them depicted here. The only difference is that the target variable is of a different type. For classification, it is discrete. It's maybe a binary variable with states yes and no. Did the customer buy? Yes or no? That is classification analysis. And in regression, you predict a quantity. Your target is a number. What was the amount spent? 20 euros, 25 euros, 133 euros. It's just a numeric target variable. This is how classification and regression differ. And, well, you can grasp that this scaling level, how it's called, the scaling level of the target variable will determine or impact this optimization of fitting the model to the data. If you have a discrete target, which is yes or no on those multiple states, Yes, no, maybe. The way you measure fit will differ from the way you measure fit if you try to predict a number, sales or purchase amount, where you could use something like least square. Differences are not that much. In terms of how the models work. How we evaluate model will again differ more substantially between regression and classification models, as we shall see. But that's pretty much it, how these two differ. I will focus a bit more on classification models in the course, just because I believe that other courses, for example, my colleagues in econometrics and statistics, emphasize a bit more the type of regression, the regression type of models. You get to see more of these in other courses, hence I focus a bit more on classification models where we predict discrete variables. But again, differences are not that substantial, so you really don't need to worry about it. Okay, that's as far as the intro part goes. Sorry for this long monologue. Let's look at some applications here. Schufa is trying to predict credit risk. Okay, but what is credit risk? Talk about algorithms, we need to be very specific what we mean. So what is credit risk? And we could then rephrase that question. When Schufa builds their models, their risk models, what type of data do they feed into their models? More specifically, in the data they feed into their models, what really is the target, the label, the target variable that they consider, that they show their algorithm. What is the target? And this will always answer the question, is it a regression or is it a classification model? So what was the target in the Schufa example? In the typical way we think about credit risk modeling or default modeling, we envision a binary target, which is exactly whether somebody has failed to pay back a loan in the past. Partially or completely. Normally that is not distinguished. A vanilla probability of default model distinguishes lenders who fulfilled all their credit obligations in the past and those who did not, who failed to do so, who missed certain payment. Display the default event and then the target is binary. And if it is binary, we know it's a classification model. It's not the only way to do it. We could approach the same type of question, estimating the risk of lending to a customer, using a regression model. That's absolutely possible. It's not the prevalent approach, though, and it's not the approach that credit bureaus like Experian, Schufa, and all the others follow. Let's consider a different application. Product return management. The reason why I picked this application is that it is waiting for you at Kaggle. Our working task, our mini assignment, which I must not call like that, basically concerns this use case, which is a known problem to every e-tailer. Zalando was struggling. They were really struggling with the return problem for a long while, which hindered them to make any profit, because they were always popular. They used this massive marketing strategy to popularize their label, their brand, to get their brand into the mindset of consumers. So sales figures were quickly at a very nice level, but the profit, that was the problem. And the problem here was that people bought a lot, but then sent back all these shoes. And you can imagine with shoes, it's delicate. Often they don't fit, and then you immediately send back the product. And there are other reasons. That's product return, and the return management embraces all the strategies that an e-shop can take to prevent customers from returning items they buy and cut the cost to handle the returns. And we can imagine, right, these costs are massive. First, well, maybe we offer free shipment. Well, not essential, but maybe we do that for premium customers. So we pay our logistics provider to ship the good to the customer. If you follow the website I'm quoting here and pay attention to these infographs, some of these infographs, they emphasize how customers typically expect free return opportunities. So if an e-shop does not offer a free return policy, that's going to deter customers from buying in this shop. So as an e-tailer, you sort of have maybe to offer the possibility to return items for free. So you pay your logistics provider twice, first to ship the good to the consumer, then to return the good from the consumer to yourself. And then there is all the packaging, which involves additional costs for you. So it's really costly, and cuts into your margins, these return problems. And what shops do, what Zalando, amongst others, uses in order to address this challenge, the return challenge, is using predictive analytics. They have highly talented people, top data science team, which, well, among other tasks, looks into the product return management. Trying to forecast which customers are going to return, or, slightly different perspective, which products in an order are going to be returned. What ways do we have here to define our target? How could we define our prediction target for predictive analytics? Remember, algorithms are very, let's not say stupid, but stubborn. They want their data in a table with a label column and other columns. This is what they want. You don't give it to them, they just say no. Computer says no. Okay? So how can we frame this as a prediction problem that complies with this type of data structure? We imagine there are two groups of people, you're saying. So the entity of your modeling are people, customers, which is possible. And then we distinguish those who are going to return and those who are not going to return. And when saying return and not, what type of horizon do we have in mind here? This fundamental approach again for orders that occurred in the past. We know whether items were returned. So using this information, we can label past orders. Please note, we are now talking about a slightly different subject that we model. Orders as opposed to customers. That's a decision we need to make in modeling. What is the right subject level? You could maybe call that. Do we model customers and predict customer behavior, whether customers are going to return something? Do we predict at the order level? What's our level of prediction? But okay, it's important to note, you're saying for the past, no matter whether we consider customer level modeling or order level modeling, we know whether something was returned or not. We can frame that as a yes-no type of question and then use a classification model. Then we would then run this model. When do we apply that in operations? I believe, and this is my understanding of what you should do, well, you would run that for every order or customer that's currently ongoing. So somebody surfing the web shop, putting items in her basket, eventually moving closer toward checkout. And at some point in this process, from first visiting the shop, browsing different products, adding items to the basket, all the way to checkout, somewhere in between, you want to run your models, or maybe multiple times, run your models, create prediction of return probability. This is as far as the when part is concerned. And as an example, this could deliver you at the point of the checkout process. So the final web page where you summarize your order, display the customer what she has bought so far or what she is about to buy, where At the low end, we see the button buy now. At this point, you as a shop owner would know what's the probability of an item in this order being returned. And here again, maybe you know that at the item level, so you create prediction for every single item in the basket, or else you could imagine carrying out the prediction at the basket level. For instance, for the whole basket, whether one or more items are going to be returned or not. That depends. Both is possible. How is this information useful? You said, I would use that for pricing. Knowing from surveys, from market research, that customers value free return shipping, we could say, oh, we have a free return policy. And in fact, we have that for some products. And for others, we just do not offer free return policy. For certain products, we let the customer pay for shipping items back to us. And then we use prediction models to determine where do we offer free shipping, i.e. whenever the return probability is very low, it's not so costly to offer free return shipment. And for items where we know the return likelihood is very high, we don't offer that. That's possible. Now think, is it good, is it bad, is it ethical, is it efficient? That's debatable. But from a data science perspective, that's absolutely feasible, and it's one use case, how prediction could create value. One cost factor that we face is warehouse costs, inventory costs. It's a huge cost driver for online shops. I mean, one of your USPs is that you can offer the long tail products, those products that you don't find in bricks and mortar stores. That's the key advantage of online stores. But you need to be excellent in logistics in order to do that. And you're saying, well, knowing that certain items are going to come back eventually, we can cut our inventory levels for those items. It's a possibility. Well, you would need to discuss that with stakeholders at Zalando, whether they like it or not, or other shops, right? There are advantages, there are disadvantages, but it's a proper predictive analytics use case for sure. The problem with your approach, or a potential problem, would be the items that we get back. Can we really resell them? Are they in a state that facilitates reselling? If it was a piece of clothes and it just didn't fit, it's properly returned in a proper shape, we just repackage it and then can resell it. And then you're saying, for those items where we know that the return probability is high, why don't we use this insight to revise our packaging? Maybe try to come up with more sustainable and or cost efficient as well, whatever your objective is, ways of packaging. What we do know for sure, an item that gets back to us, we will need to repackage it before we can resell it. Hopefully we can resell it, hopefully, but in any case, repackaging will be needed. So let's try to optimize this. I haven't seen any examples so far. All the examples you gave were useful, for sure. I haven't seen any example, I believe, that tries to prohibit returns. That's maybe the primary objective of the shop, preventing returns from happening. What can we do here? Customers return items for various reasons. One reason, specific to clothing, certainly is fit, sizes. So you could score items for the return probability and then try to inform the customer, knowing that, oh my God, he's going to return that anyhow. Trying to, nudge the customer to not buy in the first place or buy something else, maybe a larger size, maybe a different color as well. Red shirt, green pants. Are you sure? not going to look well, I tell you. You're going to look like Freddy Krueger. You can try to really nudge customers to not buy items where you are very certain or pretty certain that they're going to return that anyhow. That's a possibility you have. Okay, so sum up. Useful for various reasons. We can try to predict return at the item or customer level. We can frame that as a prediction problem. Our thinking goes mainly into classification models, which are indeed more prevalent in industry for this type of use case. We could possibly also frame that as a regression problem, but we can frame it as a prediction problem. And then we discussed ways to use the output of our models, their decision support contribution to redefine our processes, optimize our business processes in various ways. More focused on cost cutting, more focused on reshaping the customer experience, more focused on sustainability, all very well goals, very good goals with you. So this is how we phrase that as a prediction problem, just using our standard modeling approach. I also thought about the probability of return as our prediction target. We could imagine a binary target variable, product was returned or not. Create models that output a probability for that. And we discussed how that can be useful. All right. In all these examples, and especially if you want to nudge the customer to not buy, you believe this shirt is not going to fit. I rather have him not buy it, possibly losing some revenue, but I'm fairly sure it's going to be returned. So the expected revenue is less than the expected cost of the handling the return. I want to nudge him to not buy. You need to determine how high the probability of return should be before you nudge the customer to not buy. Normally, after a prediction, there is a decision to be made based on the prediction. It's normally a chain. I'm depicting that here. The decision could be any nudge to prohibit the purchase, not offering free return shipment, displaying a pop-up window saying, we believe this product you might not like this product, consider picking another one. And we could envision other nudges. But we need to decide when we really fire them. When do we show this pop-up window? When do we just not allow free return shipment? When do we artificially increase delivery time to a period where we are certain the customer is going to not buy anyway? We just say, oh yeah, nice, well chosen, I can ship this product in 3 weeks. So if you now purchase a Halloween costume, for example, and the shop tells you 3 weeks from now, it's not going to be useful. There are various nudges. But when do you fire them? You need to come up with some threshold. How high your forecast you need to be before, firing the nudge or generally making the decision. I'd like you to keep this slide in mind. We'll elaborate that in more detail in subsequent lectures. But this is our first contact with another fundamental thing in predictive modeling. A prediction is different from a decision. It's not the same thing. There could be much overlap. The prediction can, in some cases, almost equate to the decision. Typically, however, it's not the same thing. It's a chain. Prediction comes, we compare the prediction to a threshold. Based on this comparison, we make a decision. So just for all of us, this is very important. You were asking, so these use cases you discussed, they touch upon really sensitive issues. You actually, I was suggesting to actively prohibit a customer from buying. That sounds bizarre if you think about it. From a marketing perspective, this is bizarre. Marketing tries to achieve the opposite. We want people to buy, and we don't want people to not buy. Right? So you're asking, what about the error of these forecasts? We forecast the future. That's prone to error for sure. So as a user of predictive analytics, you will basically set up processes to monitor your model, monitor them to then assess ex post how well they predicted. And then by monitoring the ex post performance of your model, judging when it is time to revisit, revise, update your models. Or in the worst case, abandon them altogether. This monitoring is difficult for many reasons. We learn about the standard processes in the subsequent weeks, but this example nicely reminds of one fundamental problem in model monitoring. If we actively prohibit a customer from buying, we will never observe what would have happened had she bought. Impossible. We can observe whether a bought item is going to be returned. That's something we can observe. We cannot observe whether an item that wasn't bought would have been returned. Had it been bought? It's impossible. The same problem occurs in other use cases. Think about the super example again, credit scoring. Our decision, or the decision of many financial intermediaries, is we can lend money to the customer. Here's an application. Customer wants money. I can lend the money, earn interest, but face the risk of a default and a loss. My decision is to lend or not to lend. That is the question. If I lend money, I would observe whether the customer pays back or defaults. If I don't lend money, I will not observe what's going to happen. This complicates. It's a counterfactual problem, really. We don't observe the counterfactual. It's a very interesting stream of research, counterfactual inference, trying to make inference about what you cannot observe. One reason why this is complicated, but you can certainly trace, that's much easier, whether your models do well on forecasting returns on the past data, and then you can hope that if they succeed on the past data, this success will generalize to the future, at least to some extent. If you continuously monitor the performance of your model, you will hopefully be able to detect a decrease of model accuracy, which then triggers action to revise it. And prohibiting the customer from buying is certainly an extreme use case, and use cases that are more likely and that you've seen, if you think about it online also, are ways trying to migrate you to alternative products. These shopping agents or assistants, in some years down the road, we will probably have virtual shop assistants who are trying to consult us. Now it's maybe just by Windows or other means. Amazon, for their clothing shop, they sort of recently deployed this solution where you can basically create a profile for yourself. How tall are you? What's your weight? What's your age? What's your gender? And then they basically compare that to return data, trying to make recommendations. There are milder ways to fight return management, where you also, however, need a forecast for many of these ways, right? So that's model monitoring. And for the decision, before taking ads, you need this threshold. This is also how banks operate. You get your credit score. Your credit score is compared to a threshold. If you're above, you get the money. If you are below, bad luck. And this threshold is an element that has nothing to do with predictive modeling. Or it should not be, it does have something to do. But I find it important to see the threshold as an ingredient in the modeling process that comes from the business. How do you know whether you should prohibit the customer from buying? You ask me, and then as an economist, the answer is trivial. You compare the expected revenue to the expected cost and judge which one is higher. As easy as that. Well, theoretically. You know the margin on the product. You multiply that with 1 minus the return probability that comes from your model. That's your expected benefit. You hopefully have from accounting an estimate of what it will cost you to handle the return. You multiply that cost with the model estimated return probability. There is your estimate of the cost. And then you maximize your expected value. In a nutshell, this is how you can basically proceed here. Providing accounting is set up such a way that you really know this information. What's the cost of handling return? Sounds like a trivial question. It's not. Something that many companies will have difficulties to give you a crisp answer. Worse in finance. What's the cost of a bad loan? That's something you can ask a financial analyst to make her sweat. Often accounting is just not set up to, provide with information on the level of an individual loan. As a product line, maybe yes. But much of predictive modeling is focusing on fine-grained, detailed decision like return probability on an individual item level, or behavioral predictions on the level of an individual customer. Not a customer group, not a market segment, no, the level of the individual customer. That's basically the paradigm shift in the big data age. We are trying to leverage the vast amount of data we have to create predictions and make decisions on more detailed levels. Or individualize our marketing communication to the level of the individual customer. Sending Mary a different email newsletter than we send John. So to be able to do that, we need to anticipate what Mary likes and what John is interested in. This is an example for an individual level, customer level prediction. Okay, right. I wanted to run a little poll about other use cases of predictive models. To save some time, here are some examples. And they are not arbitrary. Each of these examples is popular. It's maybe biased toward my interests or few things I know maybe. There are numerous applications. E-commerce analytics, see that as an umbrella term for stuff like return management, but also couponing. When do I offer a discount? E-commerce, that's easily done. Pop-up window, buy now to get 5% off. Costs of doing that are zero. You just display this pop-up window. Technology is readily available. Zero cost. Should you do that or not? How could we frame that as a prediction problem? How could we use basically predictive analytics, and what type of predictive analytics, to create a system that automatically or semi-automatically displays coupon in online shops? So you're considering, for example, the items the customer maybe has in her basket already, or at least has looked at in her browsing session. Based on that, you predict the buying probability. Compare that to a threshold again, right? And you're suggesting that when you get close or beyond the threshold, so when you're really likely to buy, then you suggest now you offer a a little bonus, a little discount to basically sign the deal, make her buy. That's your proposition. That's a possibility. So you predict, that's what you predict, purchase probability. So what we don't, we know that we pay different prices for airline tickets and for hotels. We know that. You're buying a flight to Munich today. I buy a flight with the same airline tomorrow. I pay more than you, or you pay more than me. We are used to this price discrimination in certain industries. We really would not like seeing that in e-commerce. You and me looking at the same product at Amazon, you seeing a different price than what I see, that, at least by today's standards, I would argue, is not acceptable. Customers would basically go right. And then there is this rumor that has long been reality, this price discrimination at e-shops. And you know, there's this rumor that whenever you, I guess you know, whenever you access a shop using a Mac or some Apple device, this might signal that your buying behavior, this might signal that you're willing to pay higher prices, so it's going to raise prices a little bit. So fact here is, they clearly know which device you're coming from. When you run a website, you know for every visitor the device, and therefore it's entirely feasible. You're saying, oh, I observed this, I did a little mini experiment, and again, technically it's entirely feasible. Price variations that you observe can, however, have multiple sectors. And it's not so easy to set up an experiment at such a scale that you could really rule out all the other possible sources of variation. At least I don't know of any official statement by one of the leading shops saying, yes, we do this. Or we do price discriminations. Why would they make such statement in the first place? This is why I'm not yet willing to say this is a reality, but that evidence like yours clearly is available. And moreover, or definitely is long reality, you don't need to do that. You don't need to admit or be accused of carrying out price discrimination in that way that you make your Apple those who browse your shop using Apple device pay more. It's not essential. You can do the price discrimination the other way around. You just raise prices for everybody, and those for whom you then charge too much, you offer a coupon. That's much nicer. You lower prices. Much nicer way. You want to be the good guy. You want to lower prices, right? That's the way to do it. But it's the same thing. It just means that if you get a coupon and I don't, you pay less than me. It's the same thing. It's just easier to tell the story. And predictive modeling helps a lot because we can predict how much somebody is willing to pay. And then set prices accordingly. That is a use case of predictive analytics and in general. Maybe not the ones we like the best as customers, but it's clearly feasible. All right. Okay. So here were some other use cases. I would like you to go through these examples and try to make a case for predictive modeling. Anti-money laundering. Possibly, or one possibility is taking a transaction level perspective. You look at financial transactions going on, company, suppliers, etc. And you score these transactions according to how suspicious they are. What might be a variable describing a financial transaction? Time, reason, the amount, and since last transaction, recipient, and what's the opposite of the recipient? The sender. Some brainstorming and we could come up with things we can observe. When we can observe certain things, these could be the variables in a predictive model. We always need the columns of our table. What could be the target? Suspicious level, you said. So more detail, what's the target then? If we want to create a model that scores transactions according to their suspiciousness, So the assumption here you're saying would be to have information for the past which transaction where money was laundered and where not. So you again basically considering a binary target. Yes and no, good or bad, fraudulent, legitimate. Exactly. And that is true. You know, whenever you're trying to create a scoring model, be it in credit scoring or anti-money laundering, fraud screening, typically, and that's one of the take-homes of that slide, you consider a binary target error. Yes, no, type of question. Good or bad. That's classification. This was also what you suggested when talking about the couponing. Buying probability, buy or not. The target, the thing you want to predict, the thing you feed into your algorithm would not be something like a probability, because you can't observe probability. You can observe states. Product returned, product not returned. Product bought, product was not bought. Yes, no. So in the couponing example that you provided, our target was also a binary. This is the reason, that's precisely the reason why I have anti-money laundering here and I have also fraud detection. You know, these use cases are really the gold level. Once you get there, you made it. As a data scientist, but also as a company, in that predictive analytics depends on this target. You don't have a target, not your approach. And knowing which transaction in the past were fraudulent, tough. Really tough. How would you know? Maybe there was a court judgment. And then you can say, okay, yeah, that was a fraud because the court judgment exists. In many cases, there won't be such hard evidence. And apart from that, the court judgment might be wrong as well, right? So, knowing something with certainty in the scope of fraud modeling, very hard. So the information that we have about our labels, it's scarce and maybe not reliable. This is why these type of problems are particularly hard and why they should always be complemented with other type of modeling paradigms, anomaly detection, outlier detection. These are different types of models that can be considered and play a vital role in fraud screening. In addition to, these vanilla type of predictive models that are introduced today in the form of regression or classification models. All right. Took a while, but I honestly believe this was useful. Getting the role of predictive modeling clear before looking into algorithms. I want you to know by heart what it can do for you. Well, as a data scientist working for some company. So that is important. From now on, we will, however, get closer to the algorithms. In theory, I would have talked a little bit about decision tree learning as well. Okay, so have a look into the slides, please, for next week to prepare. And if you know them already, you can also I invite you to also have a look into the slides. Thanks a lot and enjoy the tutorial.